So today I will be presenting our work on multitask learning from unlabeled data to improve the cross-language speech emotion recognition. So in this presentation, first of all, I will motivate the problem. Then I will present my proposed architecture or proposed method, and then I will show some results and finalize my presentation in the conclusion. So what is the motivation behind utilizing the unlabeled data here? So if we see a typical speech emotion recognition system, it consists of three main components. First one is the emotional speech or features. You can use raw speech or emotional features, maybe from some OpenSmile EG maps, some MFCCs or something. And then you pass these features to a deep learning model. That deep learning model or any machine learning model you can use, that model predict the emotions. So these models perform really well when you have the data which have the distributions of training and testing almost similar. So what happens when the distribution of training and testing data is not similar, like in the case of cross-language setting? So the performance of these systems drastically in decrease, like from 80% it comes to maybe 25 or 30%, like that. So that is the main reason of working on improving the generalization of these systems. So in this work, we try to come up with a solution where we can inject some unlabeled data in the system to improve the performance. And due to these reasons, we cannot utilize this system in real life because they lack of generalization. We cannot deploy in the real life. For example, if the data is coming from some unknown distribution or some new distribution, they are unable to perform very well. So this paper mainly focused on multitask learning and then try to inject some unlabeled data in the system. So this is the overall proposed system. So we have a shared network and then we have three classifiers. So for example, here we have emotion classifier that gonna classify the emotion, and then we have a language classifier that gonna classify the language of a given speech. The third one is the domain classifier. So in here we use the domain classifier as a classifier that detect the label or the unlabeled. So data that we, for example, I will explain in the next slide. So what is the label unlabeled data? So we injected unlabeled data in these two classifiers. So unlabeled data is in terms of emotions. Like we got some data for different language from Vox, or even from YouTube. You can get data from different language, and then you can pass that data into the system along with some partial emotion data. And when you optimize the system jointly, the shared network will be learning some generalized representation or common representations that are common to all these three tasks. So if we see here, so we have some emotional data like the EmoCap, EmoDB, EMOV, and Urdu. So these are the data sets that are emotionally labeled. So we here try to classify the valence, so negative and positive, because all these data have differently labeled. So we try to map them on valence mapping. And then we also got some data like LibriSpeech and VoxForge that have just the language label. So they are really big data. So we can use a language identification here. If we see the previous figure, so we can inject the data for the domain and language classifier. When we are adding the data in the system more, the generalization of the system is increasing. So for evaluations, what we did, we use spectrogram as an input to the system. For pre-processing, we removed some silence from at the start and the end of the each utterance, or we selected like 6 seconds of audio length for all the evaluations. So first of all, we computed some baseline results. So baselines mean like we computed within corpus, like the model is trained for like same data from the database and then evaluate on the same data. So for the baseline network, we removed the 2 other components because then we have just one language data, and we remove the domain and language classifier. Just the emotion classifier with the shared network is become our baseline network. So we computed for all the data sets, and then this gives us a benchmark where we can compare when we are adding the data. Are we able to improve the baseline result in cross corpus setting? So I will show you next how we did that. So this is a cross corpus results. So here we, in the top of this table here, we have the baseline results. And then when we are using the other database for like the, this is for the baseline model, just the CNN LSTM with a single task learning. And but when we are going with the multitask learning without additional data, so without additional data, we are not using the domain classifier. Here we are just using the language and emotion classifier because the domain we don't have additional data, so we cannot classify the domain. But when we are adding the domain classifier with the additional data, our performance is almost around 4 to 5% is increasing for all these target data sets. We trained the model just for the EMOCAP, English data, and we evaluated for German, Italian, and Urdu. So based on this evaluation, we can see like when we are adding the more information in the system, our performance or our generalization is increasing. The next is what is the effect of auxiliary task or the multitask learning here. So we evaluated just one language identification as auxiliary task, or just the domain identification as auxiliary task, and we add both together. So this figure shows like adding more auxiliary tasks, more related auxiliary tasks, improving the generalization of the system, and it leads to the increasing the performance of cross language speech emotion recognition. The next is the adding the target data. So target data here, all the previous results are just we trained the model in one language and evaluated the model in another language. So we have, for example, the EmoDB, the German data. So if we are adding some small portion of samples in the trainings, what is happening? So if we see the figure, we are just adding the number of samples here in the x-axis, and our performance is considerably increasing. Here the system is able to see the sample from the target data, and then but just using 200 sample, we are able to increase the performance above the baseline we get within corpus. So it means when we are adding the data in the system, target data in the system, the model along with the additional unlabeled data, the model is able to perform really well for all 3 languages. So these are a couple of experiments, and here is the conclusion. So based on all these findings, we can say like if we have data that is labeled for one of the tasks, we can utilize that data to jointly optimize the system and can learn the generalized representations. These representations can help us to improve the performance for the main task, that is the emotion classification, and these findings are generalized to the other like other audio related task, maybe the depression detection or all these things, where we can utilize all the additional data, maybe from emotion or from maybe a speech recognition task, and then inject in the system to improve the generalization of the system that gonna help us to improve the performance. And this system, based on these finding, we can say, like, if we can develop a system with some generalized representation and then use in the real life, they can uh, able to detect some they can able to work in the situation where we have the distribution of the target data not belong to the training data. Other than, we also find, like, when we are adding the target data in the system, our performance is increasing. And when we are adding multiple auxiliary tasks, but these tasks should be related to each other, then the performance of our system is increasing. So that's all from my side. If you guys have any questions, you guys can ask. There are a couple of other things, like, for example, we can detect, you guys can hear me, right? Yeah, so what I'm saying, yeah, there are a couple of other tasks that already people explored, like you can utilize the speaker identification as auxiliary task, or even the gender identification. The gender identification is really help to improve the performance of the system for emotion, and for, I'm not sure about the other tasks like the depression detection and anxiety detection, but for the emotion, the gender really help to improve the performance. And even like some unsupervised tasks, like maybe the reconstruction or maybe the clustering as an auxiliary task, also help improve the system, because when we are adding the system more data, it always help to improve the generalization of the system. So when we have more generalized system, we always get better performance. Yeah. The main reason was because most of the studies in the literature, if you see the table,